I'm Sayed Said Masumzadeh, and in this presentation, I will explain a gossip-based dynamic virtual machine consolidation strategy for large-scale cloud data centers. There is always a trade-off between energy consumption and performance degradation in a virtualized cloud data center. If you pack all the virtual machines in the least number of physical host nodes in data center in a given period of time to decrease energy consumption, it's very likely that you degrade the performance of the application due to increase of resource demands of virtual machines inside the physical host node. So it's obvious that we need a dynamic management strategy that would be able to repack the virtual machines dynamically over time to decrease the energy consumption as much as possible while decreasing the performance degradation of the applications running on the virtual machines. One solution can act like this. In this architecture, we have a local manager per each physical host node and a computing entity as a global manager. In this situation, each physical host node can contribute to dynamic virtual machine consolidation procedure by managing itself in an overloading situation. But how? It's possible by migrating one or more virtual machines away from itself to other physical host nodes if the utilization of the server exceeds a threshold value. Global Manager in this architecture is responsible for placing migrated, but also is responsible to detect underloaded physical host node, which is one has the minimum utilization amongst other nodes. In this situation, all the virtual machine has to be migrated and the physical host node goes to sleep. The problem of this architecture is that the global manager can be a performance bottleneck if the number of physical host nodes grows dramatically in data center. In addition, the system suffers from a single point of failure. How is it possible to have a fully distributed dynamic virtual machine consolidation without having any centralized entity as a part of our management system? We proposed a fully decentralized dynamic virtual machine consolidation strategy on top of a P2P network of physical host nodes using a gossip-based protocol. In our proposed strategy, each physical host node is considered as an independent management entity, is able to make all the decisions and take all the actions about its own situation at the local scope of neighborhoods. The randomness of the system topology as a result of using a gossip algorithm facilitates the convergence of the management process toward efficiency in terms of energy and performance inside the data center. In this paper, we have evaluated our work through a cloud data center simulator that we developed in-house over PeerSteam simulator tool. Our management strategy is split into three sub-strategies: how to manage overloading situations, how to manage underloading situations, and how to manage virtual machine placements. Before starting to explain the management strategies, sub-strategies, I have to say that we just considered CPU utilization for overloading and underloading detections. However, we have considered storage, memory, bandwidth, and CPU utilization for VM placement strategy. The overutilization management is straightforward. The host doesn't need to have any information from other physical host nodes to decide when it is overloaded, so it can be done completely locally. We can define a threshold value for utilization. If the host exceeds this value, the host node is overloaded. In this situation, one or more virtual machines will be migrated until a utilization falls below the threshold. In our paper, we used a static threshold and we used also a random strategy for VM selection. Underloading management can be done through a competitive strategy, whereby a physical host node is considered underloaded if it has a CPU utilization lower than the average CPU utilization of other physical host nodes. In this situation, each physical host node needs to know the CPU utilization of other physical host nodes to make decisions. A physical host node in a VM placement management, a physical host node has to migrate virtual machines away from itself to other physical host node whenever it is overloaded or underloaded. In underloading situations, a physical host node has to migrate all the virtual machines away from itself, while in overloading situations, the migration will continue until the CPU utilization of the host node falls below the threshold value. Virtual machine placement is done by the overloaded and underloaded physical host nodes themselves. In the VM placement schema, a physical host node is selected to receive migrated virtual machines if it meets three conditions. 1. It has enough resources to place a new VM. Its CPU utilization does not exceed the threshold value after placement. And the last one, it shows a minimum increase in energy consumption amongst other physical host nodes after placement. Therefore, it's obvious that each overloaded or underloaded physical host node needs to have some information about other host nodes to make decisions. For communication reasons, the data center is established on top of an unstructured P2P overlay using a simple gossip-based protocol. The gossip-based protocol builds a time-varying randomized P2P overlay in which each physical host node has just a partial system view that we call it neighborhood. This property allows the system to scale with increasing number of physical host nodes as it does not rely on a central server. Physical host nodes can join and leave the network at any time without having any effect on the total performance of the system and also without the need to notify a central management unit. In the following slides, I will explain our gossip-based underloading detection as well as our VM placement schema. Also, we will explain how the system can tend to global efficiency when host nodes make local decisions within neighborhoods. After the overloading management process, which can be done completely locally by the respective physical host nodes, all the physical host nodes periodically check whether they are underloaded or not. Once a physical host node is added to a data center, it initializes a local parameter, let's say AVG CPU utilization, by its own CPU utilization. The process of the underloading detection schema for each physical host node is split into the following steps. Each physical host node triggers an underloading detection by exchanging AVG CPU utilization with other physical host nodes at the scope of the neighborhood. Each physical host node computes AVG CPU utilization being the average CPU utilization. And finally, each physical host node compares its own current CPU utilization with AVG CPU utilization if the current CPU utilization is lower than AVG CPU utilization. So in this situation, the host node is considered as being underloaded. By running the underloading detection schema for several cycles, the average utilization of the data center is disseminated inside the data center, resulting in the global convergence of the underloading detection. In our virtual machine placement schema, the VM placement optimization algorithm is triggered by the overloaded or underloaded host node itself within its own neighborhood. Running the VM placement algorithm at the scope of the random neighborhood facilitates the avoidance of a performance bottleneck in physical host nodes and also the convergence of the schema towards a global optimum close to a centralized approach. The process of the schema is split into the following steps. Once a physical host node considers itself as overloaded or underloaded, it initiates its VM placement optimization algorithm by checking whether it is currently receiving virtual machines from physical host neighbor nodes? If so, the algorithm is aborted. Otherwise, it attempts to acquire a lock for each member, including itself, of its neighborhood. Next, the physical host node requests the CPU utilization, the threshold value, and power state can be asleep or wake up from the locked neighbors. Once the physical host node receives the information from locked neighbors, it executes an optimization algorithm to migrate on virtual machine to them. The output is a migration map, which is run by the virtual machine monitor of the host node. And finally, after the migration, all logs are released. Acquiring a log on a neighbor succeeds if the neighbor is not already considered overloaded or underloaded, and also is not under virtual machine placement by yet another physical host node. If a neighbor node cannot be locked, it will not participate in the virtual machine placement process. The lock mechanism allows us to enforce mutual exclusion for accessing physical host node resources in case of multiple ongoing consolidations. You can find the pseudocode of the optimization algorithm inside the paper. In order to evaluate the performance of our proposed approach, we carried out simulation runs using our cloud data center simulator that we have developed in-house over PeerSim Simulator 2. PeerSim is a peer-to-peer network simulator written in Java, allowing the simulation of systems with varying cardinality. In our simulation, each peer represents a physical host node having its own simulated CPU performance counters, amount of RAM, disk storage, and network bandwidth. Each host node has a controller to manage overloading and underloading situations, as well as placement of its own virtual machines which must be migrated. In our study, we simulated a P2P based heterogeneous data center with 8,000 physical host nodes. Half of them were simulated to be HP Proliant G4 and half another were simulated to be HP Proliant G5. The characteristic of the VM types correspond to Amazon EC2 instance types, with the only exception that all the VMs are single core. The workload data of each VM is generated uniformly at random. The physical resources have been initially allocated to the random type of VMs based on the first read strategy. As a result, 46,605 VMs have been deployed in our data center. The initial allocation is same for each simulation trial, and the number of virtual machines is fixed during data center lifetime. Because of the time limitation, I have just mentioned some of the results, and you can find more results inside the paper. The results were obtained by running the proposed gossip-based dynamic virtual machine consolidation for 20 cycle simulation. These two figures compare the total number of sleep nodes and also the total consumed energy in data center at each cycle of the algorithm for different size of neighborhood with a centralized approach. The left figure shows that the gossip-based dynamic virtual machine consolidation can maximize the total number of sleep nodes and consequently achieves a good energy efficiency. You can see in the right figure, close to the centralized approach, if the neighborhood size is said to be at least 15. Neighborhood size is called here in the figures. The reason that the system with small neighborhood size cannot achieve a good energy efficiency is that in overutilization situations, physical host nodes do not have a high chance to find a proper active neighbor to place their own migrated virtual machines, resulting in either waking sleep nodes up in their own neighborhood or aborting virtual machine migration. In addition, in a small neighborhood size topologies, power switching rate, switching between sleep and wake up mode, is very high, because in these topologies, in one hand, many more cycles are needed until the overall average utilization of the physical host nodes to be disseminated across data center, resulting in switching more physical host nodes into the more physical house nodes into the sleep mode, and on the other hand, as stated, on the other hand, lots of switching into the wake up mode is also required due to lack of enough active nodes to place migrated VMs. The next figure shows the number of migrated VMs in different neighborhood size in comparison with the centralized approach. So as you see, the number of migration is almost as low as the centralized approach if we set the size of neighborhood size close to 50. And the reason is that the number of migration increases by decreasing the size of neighborhood, is that decreasing the neighborhood size will increase the power switching rate and consequently increases the number of migrated virtual machines in data center. So let me conclude. We proposed a fully decentralized dynamic VM consolidation strategy on top of an unstructured peer-to-peer network of physical house nodes to be used in huge data center. Dynamic virtual machine consolidation, our dynamic virtual machine consolidation can be used by physical house nodes only within the scope of their neighborhood. This type of dynamic virtual machine consolidation that we proposed works only within the scope of their neighborhoods, allowing the system to be scaled by increasing the number of physical house nodes and virtual machines inside the data center without any centralized global system knowledge. In our system model, the physical house nodes can leave the data center because of failure or be added to the data center when you want actually to increase the resources without having any effect on the global performance of the virtual machine consolidation process. And finally, our result illustrates that our proposed strategy can achieve global efficiency in terms of energy and quality of service very close to the optimal centralized approach if the neighborhood size is selected large enough. Thank you so much. Have a good time.